Here we go, and we're going to start it off once again with a video. So let's go, video.
Polychaete worms are incredibly good at finding interesting ways to survive in extreme environments. The deep sea is pitch dark with tremendous pressure and near freezing temperatures, but an astonishing assortment of polychaetes have been observed thriving in and on the sea floor. This unusual onuthid worm was recorded in the Gulf of California at a depth of 1,700 meters. That is 170 times the atmospheric pressure we feel at sea level. The animal builds a chitinous tube, but does not lead a sedentary life, as might be expected of a typical tube dweller. It can hoist up and carry the entire tube to travel across the muddy bottom at a surprisingly rapid pace. Cold seeps are areas on the seafloor where chemical-rich waters seep up through the sediments. Light does not reach these depths, so worms living here have specially adapted to survive on energy derived from chemicals in the Earth's crust, rather than energy from sunlight. These polychaete worms, called lamellobrichia, grow very slowly and may live up to several hundred years old. Hydrothermal vents are certainly one of the most extreme environments existing on this planet. Scalding hot water jets from underwater volcanoes in places where cracks form in the Earth's crust and new seafloor is created. The resulting chimneys can be completely covered in polychaetes. The most noticeable inhabitants are the magnificent tube worms like Riftia, which can reach lengths of over a meter long, or about as tall as our intern Corinna.
And so those are also going to be called siboglinid worms. So you can call them Riftia or siboglinid worms, as you like.
We also see fields of the more slender Oasis worms growing in lush, colorful orange and red swaths around chimneys venting fluid so hot it forms a mirrored surface. Pompeii worms are some of the most thermotolerant animals known, happily dipping in and out of active vents with temperatures as high as 176 degrees Fahrenheit, while avoiding hungry predators. Scientists hypothesize that they protect themselves from the extreme temperatures by wearing a fuzzy coat of symbiotic chemosynthetic bacteria. Another unlikely seafloor home where the inhabitants must attain energy through
Yeah, will be the bone-eating worms. We know about those bone-eating worms, Ossidax. Okay, so let's go. And so we've got 3 different extreme worms in this section. And so let's look at them. Yeah. So our first one are going to be called those Pompeii worms. It's named after the town that was leveled by the Mount Vesuvius. Long time ago, Roman writers told about this. And you can still see, the town of Pompeii is still there with all the really neat things in it. It was just destroyed, and there are a lot of dead peoples that have been mummified in the town by the hot ash from the volcano. Anyway, so this particular Pompeii worm is called Alvinella, and you can call it a Pompeii worm, or you can call it Alvinella. Either way is fine by me. And yeah, it is extremely heat-loving, and just like she said. So they have lots of these little things that are like hairs on their back, like little bristles. So they're just using those same sort of bristles that you find on any other kind of worm. But they will exude a sort of a sticky coating from these bristles. And the sticky coating attracts a particular kind of bacteria that are able to make energy from the hot gases that are actually bubbling out of those vents underneath the ocean. So think things like hydrogen sulfide or elemental sulfur, something like that. And so the bacteria will both act like a coat, like sort of a fluffy coat, and they will insulate this worm so that they can survive in these temperatures that are way too hot for anything else to, like a worm to survive. And we think they also help to feed the worm. So as long as it keeps its bacteria hot and next to a source of elemental sulfur, for example, if that's what they eat, then yeah, they will continue to feed the worm. So it's a nice little case of symbiosis related to feeding. Here's our next one. So these are our siboglinid worms, and I think these guys are great. We have one other video with them, so let's go look at that. And there we go, giant tube worm, endosymbiotic relationship. So this is Riftia, and this is our big siboglinid worm. So you can call it siboglinid, or you can call it Riftia.
Chemosynthetic bacteria have co-evolved with the giant tube worm, Riftia pachytilla, in order to survive the harsh environment around deep ocean hydrothermal vents. In order for biosynthesis to occur, the worm must deliver key substrates to bacteria living inside the worm's trophosome. Hydrogen sulfide, oxygen, and carbon dioxide are taken in by the worm through a highly vascularized gill-like plume. Riftia pachytilla has evolved unique hemoglobins that allow it to bind both sulfide and oxygen. These substrates are delivered to specialized host cells called bacteriocytes, which contain the chemosynthetic bacteria. These bacteria use hydrogen sulfide and oxygen to produce energy in the form of adenosine triphosphate. This energy is used to convert carbon dioxide into organic compounds such as glucose. Glucose is then supplied to the host, either through bacterial excretion or direct digestion of the bacteria. Chemosynthetic bacteria
so did you get that? The worm is feeding the bacteria sulfate just out of the water from these sort of sulfurous vents. The bacteria are using the sulfate and oxygen to produce ATP, which they're then using to produce glucose, and then the glucose is either leaking back out to the worm, or the worm will just digest and kill the bacteria. So I don't know if this one is completely symbiosis or if it's more like farming. I think it's a little more like farming, maybe. That thing about the modified hemoglobin, I think, is the most fascinating about these particular worms. So let's finish this, and then we'll go back to the slides.
Make life around hydrothermal vents possible. This unique ecosystem can provide insights into the origin of life and perhaps clues to possible life on other worlds.
All right, neat. Okay, so here we go. Here they are, the big, beautiful siboglinid worms. There you are, Riftia. Okay, and so they are found in association with hydrothermal vents and various other places. Their primary nutrition is from sulfide-rich fluids that are coming out of hydrothermal vents, and then they contain these bacteria, and they will use the bacteria, basically farm the bacteria to make sugar that they can then consume and break down in order to make their own ATP. So that's pretty neat. And the bacteria are actually fine. The bacteria can live without the worm, but the worm cannot live without the bacteria. So it's one of these sort of needy symbiosis type situations. Okay. And this is looking a little bit more in a little bit more detail at what's going on in here. So here we are showing treatments. So either with sulfite or sulfide, two very closely chemically related compounds, and then thiosulfate, which is another sulfur compound as well, and a control. And so this shows the amount of ATP that they are generating per gram. And so sulfite they do really well with. Sulfide they do fairly well with. Thiosulfate, even though it has all the same components but rearranged in a different way, they absolutely cannot use. And the controls are also getting no energy there. Over here, we're looking at cytochrome oxidase activity. So the problem with breathing this sulfide, basically, which they essentially do, is that you have enzymes called cytochrome oxidases, and the enzymes in us and in this worm are totally inhibited by sulfide. And so they're deliberately bringing in sulfide in order to generate energy, but these cytochrome oxidases, which are also needed as part of the process to generate energy, would be shut down and lead to death if there was sulfide around. And so siboglinid worms make this really cool substance that is related to hemoglobin, and it is the thing that is actually going to carry around the sulfite or sulfide very efficiently, deliver it where it needs to go, and as long as you have this protein around, it will protect the the metabolism. and yeah, they'll still have an active cytochrome oxidase. So yeah, that's pretty cool, right? And so this is one more of these adaptations, and I don't know. For the test, I might have you list maybe 6 different worms and their adaptations that let them do interesting things. I think that'd be a good way to do it. Okay, and so the last worm in this little section, remember I said this was a 3-for-1 section, is going to be the ice worm. And Hesiosica is the name of the ice worm. Hesiosica. And so, yeah, that is a kind of a polychaete worm, which is just, an annelid, but one that's going to have bristles on the side. And it's going to inhabit methane ice deposits. So that's what methane clathrate is. Um, so methane doesn't ordinarily form ice at normal temperature and pressure, but at the bottom of the ocean, it is very cold. And also, there are places where there's methane that is seeping out, and there's a ton of pressure down there. And with cold and a ton of pressure, you can actually crystallize methane gas into methane ice. And then when there's methane ice, that is where these particular annelids are going to live, these ice worms. And so, yeah, it's pretty crazy. What they do is they're going to sit and they're each going to have a little hole of some sort, and they use their energy to wave their body around that hole and move water over the surface. When what they're doing is they're actually trying to melt the methane ice, and they'll be living in a place where methane ice is forming, and so they'll just get onto a chunk of it and try and melt it. And as long as it forms up at about the same rate, the colony will be stable. But I think the worm really doesn't care whether or not the colony is stable; it just wants to eat. And so what they're doing is they're melting the methane, and by doing that, they can make a home for bacteria called Beggiatoa. So these guys, Beggiatoa. And these Beggiatoa bacteria eat methane. So they're, yeah, methane eating bacteria, which is really neat. And you get these even in the Gulf of Mexico. Very cool. And so the worm is going to fan the ice to stir the water around, try and melt some of that methane, so that the Beggiatoa bacteria will be able to eat the methane, and then the worm is basically farming these bacteria. It will slurp up some of these bacteria and eat them. So the worm, yeah, makes the methane for the bacteria, feeds up the bacteria till they get nice and big and fat, and then it eats them. And so, again, I don't know that this is completely a symbiosis. I think the bacteria would be just fine eating on their own without getting consumed by the worm. But yeah, it's another way that annelids can farm. So yeah, iceworm Hesiosica also is a little farmer. Very cool, I think. All right. Yep. Okay, and that's going to be the end of this particular section.